Hello again. This time we're going to do a little bit of review for the topics that we've covered so far. Basically a review over limits. So first problem we're going to look at is we have a function y equals f of x like this, and we're going to answer these for limits. So the first one, what is the limit as x approaches 0 of f of x? Well, as we approach 0 from the left and we approach 0 from the right, you see we go to two different y values. We either go to 0 from the left, but -1 from the right, and therefore the limit as x approaches 0 does not exist. Because the limit from the left, the limit from the right have to be equal in order for the limit to exist. Okay, what about the limit as x approaches 0 just from the left? Well, sort of already answered that, it's 0. Same thing as you're approaching 0 from the right, we've already answered that, -1. And if these two had been the same value, like if they had both been 0, then this would have been 0. But since they're two different values, the limit doesn't exist. Finally, what is the limit as x approaches -1 of f of x? So as we approach -1 from the left, we go to a height of 1. As we approach -1 from the right, we also go to a height of 1. And therefore, the limit as x approaches -1 of f of x is 1. Note that if the question had been, what is f of -1, the answer would have been 2. But the value at the point x equals 1 doesn't affect the limit, because the limit only cares about what your function is approaching as you get close to, but not equal to -1. So it's just where you're heading towards, not where you're at -1. Okay, this is the first review problem. Now let's look at another one. Okay, for the second problem, we're going to be evaluating the limit as x approaches 3 of x squared minus 9 over x squared minus x minus 6. Okay, first thing you should try is just to plug in your number. If we plug in 3 into the top, we get 9 minus 9, which is 0. If we plug 3 into the bottom, we get 9 minus 3 minus 6, which also adds up to be 0. Okay, and remember, when you have limit problems and your limit is going towards 0 over 0, that's an indeterminate case. It means you don't know what the answer is yet. The limit could still exist, or the limit might not exist, and you need to do some sort of simplification to find out. So factoring is what we do for this sort of problem. The top can factor into x minus 3 times x plus 3. And the bottom can factor into x minus 3 times x plus 2. Now we can get rid of the factors of x minus 3 on the top and bottom and get the limit as x approaches 3 of x plus 3 over x plus 2. Now that we've gotten rid of that factor on the top and bottom, try to plug in your number again. And this time we get 6 over 5. So 6/5 is the final answer. Okay? I've mentioned this before, but I'm going to mention it again. Usually your last step before you can evaluate your limit is going to be some form of canceling something that's going to 0 on the top and bottom of a fraction. And therefore you get rid of the 0 over 0 problem and you're able to evaluate your limit. Okay. Next problem. Let's say we have a limit as x approaches -3 of x squared plus 9 over x plus 3. At first glance, you might go and look at this and you might say, oh, that's 0 over 0. But be careful, -3, when you square it, becomes +9. Plus another 9 is 18, not 0. So the top is going to 18. The bottom, however, is going to 0. So we have a constant over 0. And when you have a constant over 0, that means that your limit is going to be going towards either positive infinity or negative infinity. And you need to stop and figure out which, especially because Since this is a two-sided limit, perhaps the limit from the left is going to positive infinity, your limit from your right might be going to negative infinity, and then your limit just wouldn't exist at all. So we need to stop and look at from the right and the left, see if we're going towards the same infinity. So let's first look at the left. Now, I could sketch the graph and show you on the graph which infinity we're going towards, but what if you can't draw the graph or don't want to draw the graph? I want to show you a way to get it without having to draw the graph and just look at the vertical asymptote. Okay, so imagine a number that is a little bit less than -3, like -3.1, for instance. Okay, -3.1, when you square it, is going to give you a number a little bit bigger than 9 and plus another 9. Well, the top is roughly 18 still. And then the bottom, if you plug in a number that is a little bit less than -3, like -3.1, and then you add 3, you still get a negative number like -0.1. So the way I like to think of this is, although the bottom is approaching 0, it's approaching 0 but from negative values. Okay? So the top we know is getting close to 18, and the bottom's getting close to 0 but from negative numbers. And so we have a positive number divided by a negative number. Therefore, since I know this has to go to either plus or minus infinity, it must be going to negative infinity. Okay? You could do some more exact calculations, like if you plugged in a number like -3.01 and plug that into the equation. You'd wind up with something that is approximately 18. The bottom would be -0.01. And then this would be -1800. You see, it's already getting pretty large and negative. And the closer this gets to -3 from the left, the closer this will get to 0, but from negative numbers, and the bigger this fraction will become, and it'll get bigger and bigger going towards negative infinity. Okay? But, you don't have to go through this calculator work. When you have a constant over 0, just figure out which side is 0 you're coming from, figure out whether your top over your bottom ends up being positive or negative, and you can tell which infinity you're going to. Anyway, so the left is going to negative infinity, and now let's look at the right. Oops, this is not equal, this is a separate problem. Limit as x approaches -3 from the right. So a number a little bit bigger than -3 would be like -2.9. And then +3 would give you +0.1. So the bottom is getting small, but it's getting small using positive numbers. And the top is still going towards 18. So we have a positive over a positive, and our bottom is going to 0. So the whole thing will go to infinity. It'll go to positive infinity because a positive over a positive is positive. Okay. So the limit from the left was negative infinity, and the limit from the right was positive infinity. Because the two infinities don't match, that means that the limit in general does not exist. So, this is a situation you commonly get in when you have a vertical asymptote and your function is going towards negative infinity on one side and positive infinity on the other, like the equation y = 1 over x. This is similar at x = -3. We have a vertical asymptote, and we're just going to different infinities from the left and the right. Okay, next problem. Limit as x approaches 4 of square root of x minus 2 over x minus 4. Okay, first thing, try to plug in your number 4, and you're going to get 0 over 0. So we need to simplify. We can't factor, so we instead have to use the conjugate, because when you have problems involving square roots, using the conjugate usually will give you, eventually a factor that will cancel on the top and bottom. So the conjugate of x, square root of x minus 2 is square root of x plus 2. So we need to multiply by that on the top and bottom of our fraction. So multiplying the tops together gives you square root of x times square root of x is just x. The inner and the outer cancel, add up to being 0. Last is minus 4. And then the bottom, just go ahead and leave factored. And then the x minus 4's cancel on the top and bottom, leaving you 1 over root x plus 2. Now plug in 4. Square root of 4 is 2, plus 2 is 4, so 1/4. So the limit is going to 1/4. All right. Next one. Okay. The limit as x approaches 0 of x squared times cosine x. Now, a problem like this is probably going to be given with a hint. They're probably going to say, prove that this limit, they'd probably even tell you what the limit is. They probably will say something like, prove that this limit equals 0 using the squeeze theorem. Okay? So I don't think I've done a problem exactly like this on my squeeze theorem video. So I think this will be a good chance to look at some problems using squeeze theorem. So how do we use the squeeze theorem to approach this problem? Here's the way I like to think about it. As x approaches 0, well, 0 squared is 0. So this part of the problem, definitely going to 0. What does cosine of x do as x approaches 0? Well, that's just going to go to 1, and 0 times 1 is 0. Seems like we don't even need the squeeze theorem to prove this, but here's how they want you to use the squeeze theorem to prove this. They want you to go that cosine of x is a trig function that always goes between minus 1 and 1. It just goes between minus 1 and 1 over and over again. So you can write down the inequality that cosine of x is always between minus 1 and 1 for all values of x. Okay? Now, the next thing they want you to do is to create this pattern, x squared cosine x, by multiplying both sides of this equation, or all three sides, by x squared. So you get negative x squared is less than or equal to x squared cosine x is less than or equal to x squared. Now, just a note, x squared is going to always be a positive number. And when you multiply both sides of an inequality by a positive number, that does not affect the direction of the inequality. So just something you have to watch out for when you're dealing with inequalities and multiplying by numbers on both sides of an inequality. You need to make sure that they're positive. Otherwise, the inequality direction would get reversed. Okay, now that we have this, we now have a pattern that we can use for the squeeze theorem. We're trying to look at what is the limit as x approaches 0 of the middle equation. Well, let's look at what happens as x approaches 0 for the outside equations. Well, the limit as x approaches 0 of negative x squared, since that's a polynomial, you can just plug in 0 and get your result, which is 0. Now let's look at the other function. The limit as x approaches 0 of x squared, well, that's also a polynomial, and therefore it's 0. We now have everything to apply the squeeze theorem. We have, f of x is less than or equal to g of x is less than or equal to h of x. And then these two outer ones are both going to the same limit. Therefore, the limit as x approaches 0 of the middle equation must also be the same value, which is 0. Therefore, the limit as x approaches 0 of x squared cosine x is 0 by the squeeze theorem. Okay? Now, as I said at the very start, if you just plug in 0, you obviously get 0 times 1, which is 0. That makes this a little bit of a boring problem. Perhaps what I should have done to make this problem a little bit harder, and this would be to change this x to be 1 over x. Okay? the proof would be almost identical, because no matter what angle we're talking about, cosine would always be between -1 and 1. And then we proceed in the exact same way. From this equation, you would multiply by x squared on all sides. And then since this limit's going to 0 and this limit's also going to 0, then the middle equation would also be going to 0. Okay? So a little bit of an improvement in the problem or complication, but as you see, the limit is still going to 0, and you prove that with the squeeze theorem. So squeeze theorem is used a lot when you have limits with trig functions, because trig functions tend to go between like two values, like sine and cosine both go between -1 and 1. That gives you a real easy starting point to set up an equation where the middle equation will be whatever function you're trying to do the limit of, and then hopefully your outside two functions will be going to the same value, and you'll be able to apply the squeeze theorem and get what your limit is going to. Okay? So usually trig functions is one common application. Problems involving trig functions end up using the squeeze theorem. But not all of them. You may just have a limit problem that involves a trig function, and maybe you have to use a trig identity. Okay, I think I have one more problem. Yeah, one last problem. And this problem deals with continuity. So let's say that we have a function f of x, which is a piecewise function, or some teachers may call this piecemeal instead of piecewise. That's the term my teachers taught me is piecewise. Anyway, x squared plus 4, if x is greater than c, where c is going to be some real number, and then our function is equal to -4x if x is less than or equal to c. And the question is, what value of c makes f of x continuous for all real numbers? Okay, so first of all, this is a polynomial. Polynomials are continuous for all real numbers, and therefore the function's obviously continuous for x's greater than c, because it's a polynomial. Now for x's less than c, this is another polynomial. It's going to be continuous there. The only concern is where these two functions are trying to meet together, which is going to be at x equals c. We need to make sure that those two functions are going to be connected to make the function continuous, where you can sort of draw through it without lifting your pen off the paper. Or the exact definition of continuity is that your limit as x approaches, well, in this case, c. So what we need for the limit as x approaches c of f of x to exist, and we need for f of c to exist, and then we need for this limit to equal f of c. Now, in order for this limit to exist, the limit from the left and the limit from the right are going to have to exist. So let's step back, but this is the definition for a continuous at c. Now for just the limit to exist at c, we need for this to be true. And as we approach c from the left, that's numbers less than c, we would use this equation for less than c, which is -4x. So replace f of x with -4x. And then if you plug in c, because it's a polynomial, so you just plug in the number, then you get -4c. Okay? Same thing for this. For x's that are greater than c, that's going to be when x is greater than c. We use the equation x squared plus 4. So this becomes the limit as x approaches c from the right of x squared plus 4, which is a polynomial, so you can just plug in c. So we get c squared plus 4. Therefore, this is a requirement for the limit to even exist, which we need for continuity. So continuing to solve this equation for c, since this is a quadratic equation, get everything onto one side, and then either factor or use the quadratic formula. Well, this is pretty easy to factor. It factors into c plus 2 in parentheses squared. Therefore, c equals -2. because then you'd have 0 equals 0. So c equals -2. Okay. Therefore, when c is -2, we're guaranteed that the limit will exist. We also need to check to make sure that at -2, the function will exist and be equal to the limit. Just double checking, if you plug in -2 into this equation, you would get 8. -2 into this, you get 8. So both of these limits would be equal to 8. Okay, and the value of f at -2, and this is when c is -2. So we're equal to c, so we use the bottom equation, -4x, so -4 times -2, which is also 8. So I've proven that the limit from the left and the limit from the right are going to be equal when c equals -2. Also, the function at -2 is also going to be the same value, 8. So limit from the left, limit from the right, and the function are equal to 8, making it continuous. And that only happens when c is -2. So now, I could have just made this a lot simpler by just explaining it this way. In order for the functions to connect up from the left and the right, we basically need for this function to equal this function at c. This function, as you approach c, you end up getting c squared plus 4. This function, when you approach c, you get -4c. And you see, we get to that equation a lot quicker than the way I did it with the limits. But, I was trying to explain it well using, the definition of continuity. But if you're just trying to arrive at this answer as quick as possible, essentially just plug in c into both of these equations, set them equal to each other. That will make them connect. And then solve for c, and you get c equals -2. Okay, so this is just a little sample of some problems to review some of the concepts that we covered in the chapters involving limits and continuity. I think I'm going to make one more video on the exact definition of the limit. It's going to be a bonus video because I don't think everyone needs to watch it, because some classes your teacher just skips over the exact definition. For completeness sake, I'm going to make one video on that, and then we'll move on to the derivative. Anyway, that's going to be it for today. Hope to see you later. Have a good day.